So I'm going to start in this presentation. I'm going to talk about analog model of particle creation in a dynamic universe whose boundary is asymptotic, whose two boundaries, uh, whose two boundaries are asymptotic flat spacetime. And the structure of this model is a waveguide whose main component basically is a superconducting quantum interface device abbreviated by SQUID. So there are two things I'm going to discuss in this talk. The one is what I understand by studying the two papers of the model, and my attempt at calculating particle number density using numerical method. So the two papers basically deals with the same model, but they look at it through two different views. One is by taking into account the detection of the particle created, and another one is the singularity of a correlation. So the analog model looks like this, and in reality, if when fabricated on the chip, it will look like this. So main reason why we focus on this um, squid waveguide is that the same thing can be done in ion in a trap systems, but this one has several advantages over it. Now, the purple boxes are Josephson junction capacitance, and they play the main role in simulating the expanding universe. And the waveguide, and in this waveguide, this is a coplanar waveguide, and here the magnetic flux travel along this line, and you can see how they correlate, how they correspond to each other. Now the first model here, the author basically assumes three conditions without which we can't go, without which we can't get the same equation as the quantum field in an expanding universe. Now, so the first is that the frequency of the circuit has to be less than the plasma frequency of squid. This condition basically implies that we are going to do the linearization of the cos term. Cos term basically arises because of the Josephson junction energy, and to expand it up to second order, we use this condition, and the system has to be operated in a region where mutual inductance of Josephson junction can be avoided. This is done because otherwise we will get an extra term, and which will lead us astray. And the third one is that wavelength of the magnetic flux should be quite small compared to this single cell length. Otherwise, we won't be able to do the approximation of summation to integration. So these are the basic terms, and C is sum of capacitance of the sum of constant capacitance and of this ground to wire system, and the Josephson capacitance. And this Lj is called kinetic inductance of the Josephson junction, and it is denoted by these. It is equal to this. Where phi naught is a expression consisting of constants, where it is basically equal to h naught by h bar by 2e, and E phi external is the Josephson junction energy. Now, if we use Euler Lagrangian equation on this Lagrangian, we get the following equation of motion. And for the quantum field on an expanding universe, has the following equation of motion. And after doing the separation of variables, we get these two equations. So you can see if we compare these two equations, they are basically the same. This one is a constant and this one is a constant. Basically, it's an integer. So you can correspond to these two terms. And the same goes for these two terms. But this term is the scale factor. So since Lj is under our control, so by using this relation, we can simulate whatever, by using this expression, we can simulate whatever kind of scale factor we want to do. And this is how the phi external is changed. By changing the phi external, the Josephson junction energy of the capacitance will be changed. So if we use a scale factor of a plus b10 hyperbolic and use these nominal values, we get the following particle number density. And the system operates in microhertz. The wavelength of the system is micrometer, and SQUID is really a nice device for detection of photons in microwave wavelength region, in comparison to the ion inner trap systems. And this is one of the reasons why this system is this may be preferred over ion inner trap analog model. Now, in the second model, we are going to detect the singularity of correlation function. System is same, but we are going to use different generalized coordinate. And due to different generalized coordinate, here we are going to use the boundary condition imposed due to these different generalized coordinate will be Newman boundary conditions. So sign of singularity will be observed. As you can see, this is a singularity which corresponds to plus infinity, and this is a singularity. The black line corresponds to minus infinity. This is the difference of the difference of the sign of the singularity will tell us whether the particle is created or we are having a simple light cone singularity. Now, for the previous case, we saw that the analytical result was obtained for a plus b10 hyperbolic. But in this case, we have to use the step functions to get the analytical results. And there is an advantage of this detection over the previous one, and that is when we do a variation in our input, the output varies linearly. While in the first case, the output varies as the square of the input. So the detection is much harder compared to this. And this model is motivated by Hawkins, the way the Hawkins radiation are detected in the Einstein boson condensate. Now, correlator is simply given by this, and this subtraction is done for renormalization. And an example is taken when T1 and T2 are both positive. Then the light cone singularity happens when this condition is satisfied, and this condition basically stands for the singularity which occurs on the word line of a photon. In this case, is x equal to vt, and here v is taken as 1. So the singularity occurs on y equal to x line. Now the other divergence occur at this line, and this line corresponds to the particle creation. And in all the cases, the particle creation singularity is associated with negative infinity, and the light cone singularity is associated with positive infinity. Now on to the second part. I try to do the numerical calculation of particle number density, and it is done as follows. We have two sets of complete functions. We can write one in terms of the other, and by calculating this coefficients, we can calculate the square of this coefficient is particle created density. Now beta k can be evaluated by simply taking the inner products. Now what we have to do is basically the um, ODE, we have to solve this ODE given two different sets of solution. It can be easily done using numerical methods, and I use Mathematica to get it done. And for a scale factor a plus this, for the this 5 plus 2 by pi 10 was eta, I get following results. It's it is kind of right, but there is some problem which I will come later. One point of reassurance is that for the line m equal to 0, the particle created is 0, which can be seen as the our field equation become conformally symmetric, and the particle created, the number of particle created becomes large for some value of k and m, and then start decreasing. Though there's, because of the error in the calculation while doing numerical solution, though maybe because of it, the solution, the beta square diverges for great value of beta and m. And now why I said that this might be right, because when I try to do the same numerical method for 10 hyperbolic case, I get this numerically, but as I have done in my part 1 BTP part 1, I saw that the analytic solution of the 10 hyperbolic case is as follows. Now it can be shown that there is a kink in analytical case. There will be a the limit at the origin doesn't exist. While in this case, while in numerically, the solution converges to 0 smoothly at the origin of k and m. So I could not resolve this issue. And the final point, which the drawback, the shortcomings of the paper, or the idea which I came across after reading the paper, is that the fabrication of circuit is not addressed in both of the paper, and the original model is actually motivated by the one which is done in 2017 for dynamic Kashmir effect, and there we use only one Josephson junction capacitance. So the issue of threading, basically when one use external field phi external to simulate the scale factor, one doesn't get the phi external get coupled to the other phi external of the Josephson junction. And because of it, there might be issue that what we are trying to simulate might not be the same as the one which is getting simulated. And this also the direction of the photon detection in the dynamic Kashmir effect is perpendicular to the one we are doing. So because of it, the photon detection is a problem, and the paper doesn't discuss this point. So that's all I have to say, and if you have any doubt about it, you can contact me on this email.